Okay, moving on to some more concepts. This next is called identifying the real zeros of a polynomial function and their multiplicity. Now zeros, when we talk about the real zeros of a polynomial function, this is a concept that is really central to what we're going to be doing with polynomial functions in this chapter. So we're going to mention zeros here, and we're going to keep coming back to it again and again and again. And so one thing that's really important to understand as we enter into this discussion, there's three words that are more or less interchangeable. When we say the word zeros, let's add an E in there. That's the same as roots and x-intercepts. So these three words, or these three terms, are interchangeable, more or less. And for what we're going to be doing, our purposes, we're going to say they're interchangeable. So when I say identify the real zeros of a polynomial function, I can also say identify the x-intercepts of a polynomial function, or I could say to identify the roots of a polynomial function. Those three terms mean the same thing. If you can understand that, it's going to help you a lot when you go to work the homework in this section. So and in some other sections that are yet to come. So what do we mean when we say zeros or roots? Basically, it's anywhere the graph of that polynomial touches or crosses the x-axis. So these 4 points right here would be the zeros of the polynomial. Maybe that's x equal -4, -1, 2, and 4. Whatever those x values are, we could call those the zeros of the polynomial, or the x-intercepts, or the roots. Just whatever those x values are. And there's there's some other kind of details that go into this, but if you can just remember that's really what'll get you to where you need to be. Now, to actually find the zeros of a polynomial, what's very helpful when we start to do that is to have that polynomial in factored form. And so if we look at this polynomial right here, f of x equals x minus 1 squared times x plus 3, the zeros of that polynomial come from the solutions of this equation right here. Whoops. So if we set that polynomial equal to 0 and solve that, we get the solutions. That equation are also the zeros of that polynomial. There's actually a typo here. This should say the solutions here are a +1 and a -3. And how do we get that? How do we know that 1 and -3 are solutions here? If you'll remember, to solve this equation, if you have x minus 1 squared times x plus 3 equals 0, you multiplied this piece by this piece to get a 0. So this times this equals 0 means one of these pieces had to be a 0, right? Either this piece or this piece. Well, if x minus 1 squared is 0, that means x minus 1 is 0, so x is a +1. If x plus 3 is 0, then -3 would be a solution on that side. So that's where we get those from. That's called the zero product property. If you multiply two things and get a 0, one of them had to be a 0. Okay. And then this down here basically is sort of the same thing we said earlier. If r is a 0 of the polynomial, then r is also an x-intercept. So up here, 1 and -3, since those are both zeros, those are also both x-intercepts. We would see the graph touching or crossing the x-axis at 1 and at -3. We could also say that x minus r is a factor of f. So again, going back to what we said up here, if 1 is a 0, then x minus 1 is some factor of that polynomial, and if -3 is a 0, then x minus negative 3 is also a factor of that polynomial, which isn't that what we had to start with for our two factors up here, x minus 1 and x plus 3. Okay, so we can easily go back and forth between the zeros of a polynomial and the factors of the polynomial. If we know that 1 is a 0, then x minus 1 is a factor, and if we know that x plus 3 is a factor, then we know negative 3 is a 0. You can just go back and forth real easily. And so practicing that a little bit, this next set of examples says find a polynomial whose real zeros and degree are given. And it says answers will vary depending on the choice of a leading coefficient. You can more or less ignore this statement right here. We'll always choose a leading coefficient of 1. So just kind of follow my lead here, and if you'll work these problems the same on the homework, you'll be in good shape. So if we have a polynomial with these zeros, negative 3, 2, and 5, okay, then what would that polynomial be? Okay, if negative 3 is a 0, x minus negative 3 is a factor. If 2 is a 0, x minus 2 is a factor. And if 5 is a 0, x minus 5 is a factor. So if we clean this up a little bit, we get x plus 3 times x minus 2 times x minus 5 to be the three factors of that polynomial. Now, does that fit the degree we were given, degree of 3? Well, if you think about it, this is an x term times an x term times an x term. If you were to multiply all of this out, here you get x times x. When you FOIL that, we get an x squared. Times another x would be an x cubed, right? And so, yeah, that does fit a degree of 3. And you could see that if you were to actually multiply this out. Again, you'd FOIL here, and you get, once you combine like terms, x squared minus plus x minus 6. And then when you multiply those together, your highest term of x would be an x cubed. Okay, so that is third degree. Now, when you work this in the homework, you need to really pay close attention to the blue text under the problem that it gives, and where you type your answer in. If it says to leave it in factored form, then you would be able to type this answer in. X plus 3 times x minus 2 times x minus 5 is the factored form. And so you can just type that straight in just like that. Now, if it doesn't say to write it in factored form, then you're left having to multiply this out, which is what I started to do here and didn't finish. So let me go ahead and finish that for you. So you'd have an x cubed minus, okay, if we continue distributing here, minus 5x squared plus an x squared minus 5x minus 6x plus 30. So you're just distributing from the trinomial into the binomial. And if you combine a couple of terms together, you get x cubed minus 4x squared minus 11x plus 30. And so this, if it didn't ask for the factored form, then this would be your final answer. So definitely pay close attention to how it wants the question answered there. And let's go ahead and run through this one as well. I've got 4 zeros. I need to form a polynomial with those 4 zeros that has a degree of 4. So isn't that going to be, see if you can get this with me, x plus 4, right? Minus 4 is a 0, so x plus 4 is a factor. Just flip that sign around. If minus 1 is a 0, x plus 1 is a factor, then we'd have x minus 2 and x minus 3. So that could be my polynomial there. If you didn't need this factored out, if you actually needed to multiply all of it together, you could start by FOILing here. You would get x squared plus 5x plus 4. You could also FOIL here and get x squared plus, whoops, minus 5x plus 6. And now the fun part would be distributing one trinomial into the other. You get x to the 4th minus 5x cubed plus 6x squared. And then you do the same thing with the 5x. That would give you a plus 5x to the 4th minus 25x squared plus 30x. And then one more time with the 4. So plus 4x squared minus 20x plus 24. And combining all the like terms together. And I just noticed this should be a 5x cubed here. Let's fix that. Okay, so we get a x to the 4th minus 5x cubed plus 5x cubed. Those are going to cancel out. Let's look at x squared. It's a 6 minus 25 is minus 19 plus 4 is a minus 15 x squared. And if we look at x's, we got a 30 minus a 20 gives us a plus 10x and then plus 24. So if it didn't ask for the factored form, this right here would be your final answer. Okay, continuing the concept of zeros, sometimes we can have repeated zeros. And what I mean by repeated zeros is, if you look at this polynomial right here, we've got like this x plus 3 squared. Isn't that x plus 3 times x plus 3 if we square in x plus 3? And so this is actually a repeated zero. Okay, that negative 3, since it has two x plus 3 factors, the negative 3 0 is repeated twice. Here, don't we have a 0 that's repeated 4 times? There's x minus 1 times itself. There'd be 4 of those there. So we can have repeated zeros, and we refer to this as a multiplicity of that 0. And don't let that word throw you. It's a pretty simple thing we're doing here. The first 0 of this polynomial is positive 2, and it is a 0. Okay, that factor appears once, right? So it's a 0 of multiplicity 1. X plus 3 means negative 3 is a 0. It's squared, so its multiplicity is 2. X minus a half means 1/2 is a 0. Its multiplicity is 4. So the multiplicity just refers to how many times that factor is repeated in the factored form of the function. So with that in mind, let's look at a couple more of these. And we won't multiply these all the way out. Just want you to see how the multiplicity works. So example 11, again, just looking for a polynomial whose real zeros in degree are given. So the first one says a 0 of negative 2, multiplicity 2. Okay, that's going to be a factor of x plus 2 squared. Negative 2 is the 0, so x plus 2 is the factor. Multiplicity 2 means we square it. 4 is my next 0. So x minus 4 is my factor. Multiplicity 1 means it's just to the first power. Or we can just leave that exponent off. It's understood 1. Now is that a third degree? X squared times x would be third degree. So we'll just leave it like that. Let's do one more here. 4 multiplicity 3. And you guys have probably got the drill by now, but that would be x minus 4 cubed. Negative 3 multiplicity 1, so x plus 3 to the first. So we can leave the exponent off. Next 0 is 6 with a multiplicity of 2. So x minus 6 squared. And the degree needs to be 6. Okay, that's x cubed times x would be x to the 4th times x squared is x to the 6th. Okay, so we do have a degree of 6 there if we were to multiply all this out. And the last thing we can look at as far as multiplicity is concerned is how the graph behaves near that 0. The multiplicity tells us a lot about what that graph does at that 0. And remember, a 0 is the same as an x-intercept. So the way it breaks down, if the root has even multiplicity, it touches the x-axis at that root. So maybe here, let me do that better. So maybe we have something like this. At some x value, that would be even multiplicity at that x-axis. I'm sorry, that x-intercept there, because it touches. Okay, the other case is odd multiplicity. Odd multiplicity would be something like this. Okay, where it touches and then crosses over the x-axis at that 0, at that root. So even multiplicity touches, odd multiplicity crosses. And you can really understand this pretty easily too if you think about x squared and x cubed, and the shapes of those square and cube functions. X squared is a parabola shape, x cubed is that S shape. Parabola touches, S shape crosses. So that's an easy way to keep those straight. And we can see this here, x squared times x minus 2. Now, if we have an x squared, isn't that the same as x minus 0 squared? So where would the root be at x minus 0 squared? That would be at 0, right? So that's what we have right here. And since that's squared, we would expect that to touch the x-axis and turn around that 0, and sure enough, that's exactly what happens here. It touches and turns around. X minus 2 to the first is odd multiplicity, and that crosses right there. So even multiplicity touches, odd multiplicity crosses. We can actually do better than knowing whether it touches or crosses. We can know how that graph touches or how that graph crosses. When I say how, what I mean is, okay, if it's crossing, is it going from the bottom up like this, or is it coming from the top down like this? You know, that's two different ways we can cross. And same thing, we can cross from the top or from, we can touch from the top or from the bottom. So we can know how our graph is going to behave near those x-intercepts. So for example, if I take that function I just looked at, but then also take y equal negative 2x squared, and if I graph those together, let me just do that real quick. So one was x squared times x minus 2. The other was negative 2 x squared. Now if I graph those together, okay, there's my original, and there is negative 2x squared. Now what I want you to notice is this area right here. Those two graphs basically match up. I mean, they're, for all intents and purposes, at this x-intercept, they're identical. Okay, they're right on top of each other. So that's pretty interesting. Okay, that we can take x squared times x minus 2, and near this x-intercept, get something simpler, negative 2x squared, that matches it. Okay, and I can actually do a little bit better too. If I look at the graph 4x minus 8, notice what that 4x minus 8 does. It lines up almost identically with the other x-intercept. So I've got my original function, then I've got these other two, negative 2x squared and 4x minus 8. Those are simpler polynomial functions that tell me what this graph's doing here. So at this x-intercept at 2, I know this graph behaves like 4x minus 8. What does that tell me? Well, it has a positive slope, right? 4x, 4 is the slope there. Positive slope means it's crossing from the bottom going up, increasing from left to right. On the same note, negative 2x squared, I know that since that's negative, that is upside down. It's been flipped over, and so that's touching the x-axis from the bottom. Now, the big question, of course, is where did I get negative 2x squared and 4x minus 8? Did I just pull those out of a hat? Like where do you get those nice, simpler functions that tell you how this thing's behaving? Okay, so let's look at that. Where did I get these? Because you can actually come up with these. There's no guesswork involved. I'm going to skip past some of the notes here. So yeah, big question. How do we know to use negative 2x squared? Well, think about this function. It was x squared times x minus 2. I'm thinking about, okay, I want to know how this thing behaves near the x-intercept at 0. So that came from, I'm asking, okay, near x equals 0. Which factor did that come from? That came from this factor right here. So what I'm going to do is I'm going to leave that factor alone, and I'm going to plug in this 0 everywhere else. So if I do that, leave the factor that 0 came from alone, plug in the 0 here for this x. If I simplify that, don't I get negative 2x squared? And isn't that what I used to kind of match up on that function at x equals 0? Okay. Alright, so similarly, we can get that 4x minus 8 as well. Again, starting with my original function, I'm asking, okay, near the other 0, how does this thing behave? 2 came from x minus 2, so we leave that alone and plug in this value 2 into the other x's in the function. And if I simplify that, that's 4 times x minus 2, which is 4x minus 8. So there it is. So it comes from looking near one of the x-intercepts, leaving the factor that x-intercept came from alone. I didn't change x minus 2 here. Plugging in that x-intercept into your other x's in your function. And it'll take you a few tries and practice that out to get it all straightened out. But once you get the hang of it, it's not too bad. Okay, next concept, turning points. This is pretty simple. Turning points are exactly what you think they are. You can think of them as local minima and maxima. We've talked about those before. The peaks and valleys in the graph. And there's a really simple concept that says if you've got a polynomial function of some degree n, your graph will have at most n minus 1 turning points. So basically, to find the maximum number of turning points, subtract 1 from the degree. It's 1 less than the degree. So on that previous function we were working with, go back here, this guy right here, that's x squared times x minus 2. That's a third degree. And what turning points did we have? We had a turning point here and a turning point here, right? 2 turning points, that's 1 less than our degree. Now notice it doesn't say you will have 1 less turning point than your degree. It says you'll have at most n minus 1 turning points. and that's an important detail there. You could have a polynomial function of degree 4 that only has one turning point. Okay, just to kind of show you that. What about x to the 4th? It's 4th degree, right? But how many turning points are there? Just one. So at most that many turning points. And the last concept we'll look at here is in behavior. And what in behavior is, it's basically what the ends of the graph do, the far left and far right ends of the graph. So what do the ends of the graph do? Really what happens there is it matches whatever term determines the degree of your function. So as an example, again working with this same function here, if I have x squared times x minus 2, if I distribute that, I get x cubed minus 2x squared. Now which term determines the degree there? It's this guy right here, x cubed. That means my in behavior will look like the graph of x cubed. X cubed looks like this, right? So that S shape. Okay, so I know that the ends of my graph are going to look like that. The left edge is going down, the right edge is going up, is what I'm referring to there. It just tells you which direction the ends of your graph are going to go. Left edge down, right edge up, which is exactly what we see. Again, if we go back and look at the graph there, the left edge goes down, the right edge goes up. Okay. And there's really only 4 options for in behavior. Both ends go up, both ends go down, or they go in opposite directions. Left side down, right side up, left side up, right side down. Okay, those are the 4 options for in behavior. And doesn't that go back and match up with what we talked about on power functions? There's the even and the odd power functions, right? So it's the same idea there as the power functions. We're just looking at that largest term of that polynomial.